Each star you see twinkling in the night sky is a luminous sphere of superheated gas much larger than any planet. And each has a story to tell. A traumatic birth, a life on the edge.
Gravity collects the star in the first place, and then gravity wants to crush it.
And a death that rattles the heavens.
The whole thing goes off in a blinding flash, the biggest explosion in the universe.
The universe at its most volatile and action-packed. Life and death of a star. Like glittering cities in the desert, galaxies arise out of the great darkness of the universe. Galaxies made of billions of blazing lights called stars.
There are billions and billions of stars. In fact, in our galaxy, there are 400 billion stars just in our galaxy.
But how were these stars born? How will they die? And how can it be that all human beings on Earth owe their lives to the deaths of stars? The quest for answers begins here in a cloud of dust and gas, hovering in the interstellar desert. You are looking at the pillars of creation.
The pillars of creation are a stellar nursery. New stars are in the process of being born in the central regions.
Located 7,000 light-years from Earth, the pillars are part of the Eagle Nebula, which is just one of billions of star-forming regions in the universe. The pillars are towering clouds of dust and hydrogen gas.
If you remember the periodic table of elements from chemistry class, you have the light elements up at the top, hydrogen, helium, lithium, this sort of thing, and then the really heavy ones as you get lower down.
It's hydrogen, the lightest, simplest, most abundant element in the universe, that is the key component of stars. Within a nebula, clumps of this gas and dust slowly coalesce into smaller clouds over millions of years, pulled together by a very familiar force.
The same force that connects us here to the Earth, that keeps us on the Earth, gravity, is the same force that pulls things together in a way that gives us planets and stars and galaxies in the universe.
Gravity, in many senses, is the most important force in astronomy. And when gravity acts in the universe, one of the basic things that it produces is stars. Stars are sort of the most basic unit of mass that is produced when gravity pulls mass together.
Each contracting cloud can produce anywhere from a few dozen to thousands of stars. To form a star like our sun, which is 1,000,000 miles across, it takes a clump of gas and dust 100 times the size of our solar system. These clouds start off their lives bitterly cold, with temperatures hundreds of degrees below 0 Fahrenheit. But as gravity fragments and compresses them, the heat begins to soar. Within a few 100,000 years, the cloud spins into a flattened disk. Gravity coalesces the center of the disk into a sphere, where the heat rises to a scorching 2 million degrees. This glowing system is now known as a protostar. 10 million years later, the searing hydrogen core of the fledgling star soars past 18 million degrees, and something incredible happens. The core becomes so hot it can sustain thermonuclear fusion.
Thermonuclear fusion. It's a lot of syllables, but it just means it's hot there, and small atoms become big atoms.
Hydrogen atoms are moving fast enough that they actually will fuse together and will form a helium atom.
It's this nuclear reaction that produces the energy to power the star throughout its life, giving it a constant source of light and heat.
It's self-luminous, generates its own heat, and that's the essence of what makes a star a star.
If you've got fusion, you've got a star.
Once born, a star's life will be a constant battle, an all-out war against gravity.
Stars are also trying to hold themselves up against gravitational collapse. Gravity wants to crush the star down to the middle.
For stars, nuclear fusion provides the rope in the form of pressure.
The heat gets all the particles in the star moving around quickly, and they bang outwards, and that produces a pressure which can actually hold the star up against gravity. The amount of pressure pushing out on the star just matches the amount of gravity pulling in on the star, and it can sit there and burn happily until something changes.
A star will spend most of its life in this state of equilibrium. It's a phase scientists call the main sequence.
So our sun is in the main sequence. We're very happy it's in the main sequence. It provides us the same amount of energy almost every day. And that's what makes life possible.
All stars on the main sequence aren't alike. Some are much smaller and cooler than the sun. Others much larger and hotter.
So it turns out that how hot something is related to the color of the light that it emits. So a star like the sun, most of the light that comes out from the sun is sort of a yellow type color. If the sun were much hotter, the predominant wavelengths of light would come out into the blue or even into the ultraviolet. And cooler stars emit more red light.
Small, cool red stars like Proxima Centauri, the nearest star to the sun, are known as red dwarfs. They can be as little as 1/10 the mass of the sun, with surface temperatures thousands of degrees cooler. Red dwarfs are the most common type of stars in the universe.
There are many, many more of these sort of very dim red dwarfs floating out in space than there are stars like the sun. Now, of course, when you look in the night sky, you don't see the most common kinds of stars. You don't see these red dwarfs because they're so faint. You merely see the very rare, very bright stars that turn out to be very, very far away.
On the opposite end of the spectrum are the large blue main sequence stars. Averaging a surface temperature of 45,000 degrees Fahrenheit, they can be 20 times the mass of the sun and 10,000 times more luminous. In the life and death of a star, size definitely matters.
Mass is the fundamental thing which drives the life history of a star.
The more massive stars live much shorter lives than the less massive stars. And that's perhaps a little bit strange sounding, because the massive stars have more fuel to burn. You'd think they'd live longer.
So it's counterintuitive that more massive stars will burn through their fuel more quickly than the lower mass stars.
5 billion years in the future, our sun will reach this critical crossroads. Its supply of hydrogen fuel will have been completely exhausted. Nuclear fusion will cease, and gravity will begin to crush the star. At that point, the situation is desperate. In order to survive, a sun-like star must find a new source of fuel. It has helium on hand, but in order to start burning helium, the core has to be 10 times hotter than it was during its lifetime burning hydrogen.
It won't be able to fuse that helium into heavier elements like carbon and oxygen until the core gets sufficiently hot. And that's because it's harder to get the helium nuclei close enough together for the strong nuclear force to take over, grab them, and cause them to fuse together.
As it continues to contract inward, nature throws the star a lifeline. The core actually becomes superheated by the very gravitational pressure that's trying to crush it. When it reaches 180 million degrees, it can start fusing helium into carbon in a desperate gamble to survive. The star, which took 10 billion years to burn through its hydrogen, now powers through its supply of helium in a mere 100 million years.
And then the action begins. It runs out of hydrogen, starts fusing helium. Runs out of helium, attempts to fuse carbon and will fail. But all the action, all the, well, what's going on now, happens in the last 10% of a star's life.
The searing heat of the helium burning actually causes the outer layers of the star to swell.
At that point, the outer atmosphere of our star will be held in by gravity so weakly that it'll start sort of just evaporating away. Through a series of what I call cosmic burps, it will actually eject the outer envelope of gases, which are only weakly held by gravity. That'll send some shells of gas outward, illuminated by the hot central star. And that will cause what's called the planetary nebula phenomenon. Beautiful shells of glowing gas surrounding the dying core of our sun.
With the core unable to muster any more nuclear fusion, can it possibly survive gravity's crushing grip? As a star the size of our sun dies, it ejects its outer layers. With no nuclear reactions to generate outward pressure, gravity gains the upper hand. The star begins to fall in on itself, like a climber too tired to hold on to his rope.
There's one possibility that the rock climber might be able to use if he gets too tired to hold on to the rope anymore, and that is if he can find a ledge on the rock that he's climbing. Gravity can pull on him all he wants, but the ledge itself will support him against gravity, and he doesn't have to provide any more energy to win his fight. There's a certain kind of star, and our sun is actually an example of this, where the star finds that it has an out in this fight against gravity.
The contracting star finds its ledge in a surprising place: electrons, tiny negatively charged atomic particles.
Electrons don't like being compressed so that they're very close to one another, because electrons effectively don't like each other.
If you compact the electrons hard enough, the pressure of the electrons themselves is able to hold up the star against gravity.
When the core of our dying sun-like star is crushed to about the size of the Earth, this so-called electron degeneracy pressure takes over. Gravity can collapse the star no further. It's left to slowly cool into a bizarre stellar remnant known as a white dwarf. Like this one, Sirius B, which can be seen only faintly aside its companion, Sirius, the brightest star in our sky.
The white dwarf has about 300,000 times the mass of the Earth, compressed into a volume the size of the Earth. If you had just a teaspoonful of material, it would weigh several tons. So it's really amazing stuff.
A white dwarf is the final stage in the life of a sun-like star, but it's not quite dead yet. It will continue to shine for billions of years as it gradually radiates away a lifetime of energy.
I like to call white dwarfs retired stars, in the sense that all of the light that they are shining is energy that they accumulated during their normal lives.
But some white dwarfs can have one last hurrah, thanks to a friend who lends a helping hand. Because although our sun is a cosmic loner, more than half of all stars travel through life with at least one companion.
Most stars are members of binaries or possibly even multiple star systems. Close binary stars can have very different fates from your ordinary single stars.
If a white dwarf is gravitationally bound to another star as part of a binary system, it can essentially steal the lifeblood from its companion. the small but dense white dwarf exerts such a strong gravitational pull that it will start siphoning off a stream of hydrogen gas.
If it gathers material from a companion star and it is able to grow in mass, then eventually the mass of the white dwarf can reach an unstable limit, roughly 40% more than the mass of our sun. At that point, the white dwarf undergoes a catastrophic explosion, where the whole thing goes off in a blinding flash, what's called a thermonuclear runaway of the entire star.
This mammoth explosion is known as a Type 1a supernova. Although Type 1a supernovas come from exploding white dwarfs, many others, known as Type 2 supernovas, signal the dramatic deaths of much more massive stars, perhaps 8 or 10 times more massive than the Sun. Unlike their smaller cousins, when massive stars exhaust their hydrogen fuel, they have the raw power to start fusing other elements. The ashes of each set of nuclear reactions become fuel for the next, so that near the end of its life, a massive star resembles an onion in cross-section, with an outer layer of the original fuel, hydrogen, surrounding layer after layer of heavier and heavier elements.
It goes through its normal life, fusing hydrogen into helium, then helium into carbon and oxygen, then oxygen into neon and magnesium, and then silicon and sulfur. And then iron. The massive star builds up a core of iron. But fusion of iron into heavier elements doesn't do the star any good. It doesn't keep the star hot inside, because fusion of iron into heavier elements requires energy. It absorbs energy. It doesn't liberate energy. So the iron core builds up without fusing and eventually becomes unstable. When it reaches something like 1.5 times the mass of our sun, it collapses.
And the collapse is violent. Within half a second, a core the size of the Earth is crushed into an object roughly 10 miles across. For a moment, the collapsing core rebounds, smashing into the outer layers of the star and kicking off one of the most massive explosions in our universe since the Big Bang.
The collapse of the iron core blows apart the rest of the star in a colossal explosion. It's truly an amazing, incredible event.
Scientists are convinced that supernovas mean much more to the universe than spectacular light shows. They are, in fact, the source of the heavy elements that make up everything around